Okay, so now that we determined our n minus k pi groups here, we now need to determine the variables pi themselves. So how do we go about doing that? And so we do this by demanding that each pi group or pi variable is unitless. Okay, and then each pi group is defined by pi of, I'll just call it I, equals the P1 to the A times P2 to the B times P3 to the C times P to the N minus K to the, I don't know, some other variable. I'll just call that, I don't know, Q for the time being. Okay, and so these here are the repeating variables. Times the non-repeating variable, so P a non-repeating, raised to the first power. Okay, and so the name of the game then is to determine this function and to determine the powers A, B, C all the way to Q, or actually wherever we need to stop. To determine those such that P1 raised to the A power times P2 raised to the B power times P3 raised to the C power times times all of the other non-repeating variables raised to their power times the non-repeating variable in that particular pi group raised to the first power is unitless. And so this must be unitless. Okay, so how do we enforce that? And I'll just do that by way of examples. So here, for pi 1, that would equal the first non-repeating variable raised to the A power, and I'll scroll up. That is rho infinity raised to the A times the second non-repeating variable raised to the B power, that's V infinity raised to the B, times the third repeating variable, which is the diameter of the sphere, raised to the C power, times the non-repeating variable associated with that group, and that's the drag force, raised to the first power. And this must be unitless. So then to determine the quantities A, B, and C, we first write down the units, or we write this equation in terms of its units. And so in terms of units, we have 1, because it's unitless, equals the units of density raised to the A power. So that's mass over length cubed to the A power, times velocity raised to the B power, that's L over T raised to the B, times the diameter raised to the C power, that is L raised to the C power, times the drag force raised to the first power, and that has units of mass times length over T squared. Okay, and so now I'm going to rearrange this a bit, but really what we need to find is A, B, and C, such that this grouping of parameters here is unitless. So I'm going to do some rearranging here. We have 1 is equal to mass raised to the A plus 1 power times length raised to the minus 3 power plus b plus c plus 1. And so here's the minus 3. Sorry, that's minus 3a. Plus 1b. Plus another c. Plus 1. Times time raised to the minus b power minus 2. Okay, and so this has to be unitless. And so the only way for this expression to be unitless or produce 1 is if all of these powers on all of these units is equal to 0. So all powers on units equals 0. Okay, so I will write this out in equation form. So we have for the mass, we have a plus 1 equals 0 because that's the power of a. And that implies that a equals minus 1. And for time, we have minus b minus 2 equals 0. And that implies that b equals minus 2. And now for the length, we have minus 3a plus b plus c plus 1 equals 0. Now I'm going to substitute in the a that we had here and the b that we had there. Okay, and so we have minus 3 times minus 1, which is just 3, plus negative 2 plus c plus 1 equals 0. Okay, well, this is 3 minus 2 plus 1 plus c equals 0. Plus 1 plus c is equal to 0. And this implies that c equals minus 2. Okay? So then we have a is equal to minus 1, b is equal to minus 2, and c is equal to minus 2. So our pi 1 group equals rho infinity to the a power, v infinity to the b power, d to the c power, and d, the drag force, raised to the 1 power. Well, we now know what a, b, and c are, so pi 1 equals rho infinity to the minus 1, v infinity raised to the minus 2 power, d raised to the minus 2, and the drag force to the plus 1 power. Or pi 1 equals the drag force divided by rho infinity v infinity squared d squared. Okay, and so that is what the first pi group winds up being. And really this kind of makes sense because if you think back to the Bernoulli equation, the quantity rho v infinity squared, this is related to the dynamic pressure. And this d squared is related to the cross-sectional area. Okay, and so we have essentially a pressure here times an area, which gives the units of a force d. And so you can see by inspection that this is indeed unitless. Okay? And when we do chapter 9, we will see this, we will use this, you'll see this parameter again. It'll be written slightly differently. There will be a 1/2 here to turn it into a dynamic pressure, and the d squared will be changed into an a, or a cross-sectional area to make it more general. Okay? And so that's our first pi group. Now we can work on the second pi group. So pi 2. So the second pi group is equal to, rho is equal to the repeating variables raised to their respective powers, which we don't know, times the non-repeating variable raised to the first power. So this would be rho infinity raised to the a, times v infinity raised to the b, times d raised to the c, times mu, or the viscosity of the fluid. Okay? And the units of this are mass over L cubed raised to the a power, so units. So in terms of units, this becomes 1 is equal to mass over length cubed raised to the a power times L over time raised to the b times L to the c times the units of viscosity, which we found earlier to be mass over length times time. And we need this to be unitless, so we do the exact same thing that we did before. So this needs to be unitless. So we have the powers of all the dimensions, mass, length, and time. We need those respective powers to be 0. So let's rearrange this. We have a dimensionless 1 is equal to mass raised to the a plus 1 times length raised to the c plus b minus 3a times time raised to the minus b minus 1. Okay, and so we play the same game that we did before, and we need the powers of the units to be 0. So need the powers to be 0. Okay? So that implies that for mass, we look at this power for mass. That again has to be 0. So that implies a plus 1 equals 0, or that implies that a equals minus 1. We now look at length. In length, we have c plus b minus 3a is equal to 0. Well, we only know a at this point, but we don't know c or b, so we'll just leave that equation b for the time being. And then for time, we have minus b minus 1 equals 0, and this implies that b equals minus 1. So now we know a and b. Oops, b is minus 1. Now we know a and b, and I'm just gonna stick them into this equation here. Oh, and then solve for c. So then, using the length equation, we have c minus 1, which is, minus 1, not b, minus 1, this is just b, minus 3 times minus 1 equals 0. And this implies that c is equal to minus 1. Okay, so in summary, we have a is equal to minus 1, b is equal to minus 1, and c is equal to minus 1. Or pi 2 equals rho infinity to the a power, v infinity to the b power, not mu infinity, the diameter raised to the c power times mu infinity raised to the 1 power. And we just stuff these in, And we have A is equal to -1, B is equal to -1, and D is equal to -1. Or pi 2 equals mu infinity over rho v infinity d. Okay, and this parameter here is a very common one, or this parameter here is extremely common, and we will be encountering that parameter again and again and again and again. Okay, and so pi 2 is simply the viscosity divided by rho vd. Okay, and now for pi 3, because we had another one, oops, we had yet another one. Now, pi 3. For pi 3, we do the same thing. Pi 3 equals rho infinity to the a power, v infinity to the b power, d to the c power, times the speed of sound. Okay, and so in terms of units, we have 1 is equal to the units of density raised to the a power, that's mass over L cubed to the a, times the units of velocity, L over t raised to the b power, times L to the c, times L over t. And so these units correspond to rho, these units correspond to v, this unit corresponds to d, and this unit corresponds to a infinity. And so again, you need the powers on units equals 0. And again, the non-repeating variable is raised to the first power. Okay? So we do the exact same thing before, and I'm going to skip some of the steps. But we have m. So for m, we directly have a is equal to 0, because mass is only involved with this term here. For time, we have minus b minus 1 is equal to 0, because we have minus b here and minus 1 here. And so this implies that b equals minus 1. And for length, we have minus 3 times a plus b plus c is equal to 0. So the minus 3 times a comes from here, the b comes here, or the b comes from here, and the c comes from here. Okay, well, a was 0, so this is gone. And b was... Oh, and I forgot one thing on this. This should be plus 1. Okay, and we have a plus 1 for the length there. Okay, and so we know that b is minus 1 plus c plus 1 is equal to 0. Well, these cancel out, and this implies that c is equal to 0. So for the third pi group, we have a is equal to 0, b is equal to minus 1, and c is equal to 0. Or pi 3 equals rho infinity raised to the a, which is 0, times v infinity raised to the b, which is minus 1, times d raised to the c, which is 0, times the speed of sound at infinity, a infinity raised to the 1 power, or pi 3 is equal to a infinity over v infinity. Okay? So now we know all three pi groups. We know all three are n minus k pi groups. And recall that we defined this such that f of pi, pi 1, pi 2, pi n minus k is equal to 0. Or, for our example, where pi 1 equals the drag force over rho infinity v infinity squared d squared. Pi 2 equals mu infinity over rho infinity v infinity d. And pi 3 equals a infinity over v infinity. Okay, and so for our example, we have f of pi of d over rho infinity v infinity squared d squared, and mu infinity over rho infinity v infinity d, and a infinity over v infinity is equal to 0. So this is our desired function. And in general, so now we know all three pi groups. We can then yank out the one that involves our quantity of interest, which is the drag force, and we can then conclude that pi 1, which involves the quantity of interest, is equal to a function of pi 2 all the way to pi n minus k. Okay, so for our example, we have the drag force over rho infinity v infinity squared d squared is equal to some function which you need to determine experimentally or by some other means of mu over rho infinity v infinity d times and a infinity over v infinity. So this is our desired relationship. So this is telling you that the drag force scaled by a rho infinity v infinity squared d squared is equal to a function of the viscosity that should be at infinity is equal to the viscosity divided by rho infinity v infinity d and a infinity over v infinity. So, and I'll show you later how you use this information to size and set up experiments to actually measure this grouping here as a function of this grouping here and make it relevant to real applications. Okay? And I will make a note here. Note that any pi group can be raised to any power and still be dimensionless. And additionally, any pi group can be multiplied by a dimensionless constant. And still be dimensionless. So, for example, and I'll show this example for all of these three parameters here, because all of these three parameters are very common, but when you use Buckingham pi, they come out a little bit different than how they're traditionally used. So first, I'll pick on this parameter here. So pi 2 equals mu, I'm going to get rid of the infinities here, over Vd. Well, we can raise this to the -1 power. So we can say pi 2 to the -1 equals mu over rho Vd to the -1, and that equals rho Vd over mu. And this parameter here is so important in fluid mechanics, and you're going to encounter this parameter again and again and again in heat transfer and everything, and for the entire remainder of this class. This here is called RE(d), and this is the Reynolds number. Okay, and the subscript d is the reference length. Okay, and for those of you who have taken aerodynamics, you already know this, but our compressible flow, pi 3 equals a, I'm going to drop the infinities, over v. Well, we can raise this to the -1 power. Pi 3 to the -1 equals v over a. And this is the sound speed, and v is the velocity. And v over a, or the sound speed, this is the Mach number. Okay, and so you can see how Buckingham pi theorem can actually tease out a lot of these really important parameters that are used again and again, again and again and again. And then pi 1, that was equal to the drag force over rho v squared d squared. Well, this comes from some more advanced theory, but it is customary to write this as d over 1/2 rho v squared d squared, or d over 1/2 rho v squared times a, because again d squared is representative of area, and if you add the 1/2, that's the dynamic pressure. Okay, and so for some theoretical reasons, for some of these parameters, it is very common to see them multiplied by some constant or raised to some power. Sometimes these parameters will be basically raised to the 1/2 power, and don't be dismayed if you see that. There are usually some very theoretical reasons for doing that. Okay. Okay, so now I'm going to do another example with Buckingham pi. Okay, and for this example, we are doing an experiment, and we have a pipe of diameter d. I did that backwards. And at two different places, separated by a distance L, we measure P1 and P2 to get delta P. Okay, and so what we are doing is, as the fluid is moving through this pipe at some velocity v, and it has some viscosity mu, we want to we are measuring the pressure drop as the fluid flows from this pressure gauge over to this pressure gauge, because in reality there's going to be viscous effects that produce shear stress, and as we'll find out in chapter 8, that shear stress is going to cause the pressure in the pipe to drop as it flows from the beginning to the end of the tube. Okay, and it's known from the experiments that the pressure drop is proportional to the length of the distance between the pressure taps. Okay, and delta P is equal to P1 minus, not equals, P1 minus P2. Okay, and so here we're being asked to find, to use Buckingham pi to determine the effective diameter on delta P. So how do we go about doing that? So first, we are going to assume that delta P is equal to a function of the flow velocity, the diameter of the pipe, the length between the two pressure taps, and the viscosity. Okay, and so we just have to assume that, and then if you're in industry, you won't be given what it's a function of, and a lot of the problems that you'll do in class, you will be given the parameters that it's a function of. But in practice, you will have to just use your intuition to determine what this is a function of. Okay, so now we then rewrite this equation as f some function of delta P v d L and mu is equal to 0. So now we need to determine the number of physical variables, and so we just simply count them out. We have 1, 2, 3, 4, 5. So we have n equals, that's a bad n, n equals 5 physical variables. Okay, and now we need to write the units of all of those physical variables. So we have delta P of V, D, L, and the viscosity. Well, the pressure is a function of force over area, which is length squared. And I like to work in the mass coordinates, so I'm going to convert this force here into mass. So force is equal to mass times acceleration, or mass times length over t squared, and that is equal to mass over length times time squared, and the velocity is equal to, in terms of units, is length over time. The diameter is length, the length is length, and from the previous problem we found that the viscosity is mass over length times time. So we count the number of dimensions that we have. We have mass, so that's 1. We have length, that's 2. And we have time, that's 3. So we have k equals 3 dimensions. Okay, so we find n minus k equals 5 minus 3 equals 2, so we have 2 pi groups. Okay. And so, which means we have 3 repeating of variables. And in this, for the repeating variables, we cannot use a delta P because that's the quantity of interest, or QOY. Okay, and D and L have the same units, so we can only pick one of them to be repeating variables. So for the list of repeating variables, we have delta P, V, D, L, and mu. So we need to pick 3 of them, and delta P is gone. We can't use that one, and we need all of the units between all of we need all of the units between the repeating variables, and none of them can be repeated. Well, D and L have the same units, so only one of those can be a repeating variable, and one of them must be a non-repeating variable. And since we're going to determine delta P as a function of L, we will pick L to be a non-repeating variable. Okay? And so that means the repeating variables will be V, D, and mu. Okay, and I'm going to scroll up here and we're going to check the units. We pick V, D, and mu as the repeating variables, and we just need to make sure that between V, D, and L we have all the physical physical base units considered. So we have L, so that's 1. We have time, that's the second one, and we have mass. So between those 3 variables, we have all 3, and none of our repeating variables have identical units, or even units that are linear combinations of one another. So that is good. So we choose V, D, and mu as repeating variables. Then pi1 equals some pi1 function of delta P, which is the non-repeating variable, V, D, mu, so these are the repeating, and pi2 equals, and this is non-repeating, and pi2 is a function of the length between the 2 pressure taps, V, D, and mu. Okay, so again, this is the repeating. Those are variables that will be present in all of the pi groups, and this is the non-repeating. Okay, and so now we need to determine the pi groups themselves. So for pi1, we have pi1 equals the non-repeating variable raised to the first power times the first non-repeating variable raised to some power, I'll just call that A, times the second repeating variable raised to some power B, times the viscosity raised to some power, or times the third repeating variable raised to the C power. Okay, and then in terms of units, we want pi 1 to be dimensionless, so we have the units of 1, which means it's dimensionless, times delta p, which is mass over length times time squared, which is the units for that, times length over time raised to the a, times length to the b, times mass over length times time raised to the c. Okay, and we do some rearranging of this, or we have 1 is equal to mass raised to the 1 plus c times length raised to the minus 1 plus a plus b plus c times time raised to the minus a minus or minus 1 minus a minus c. Okay, and this 1 is here because it is unitless. And that should actually be not plus c, that should be minus c. A plus b minus c. Okay, very good. So now we need, to make this true, in terms of the units, we need all of these powers to be equal to 0. So need the powers to be 0. So we have, for the mass, we have 1 plus c is equal to 0. That implies that c is equal to minus 1. For time, we have, and for time, I made a little mistake. For time, that should be minus 2 over here. And for time, we have minus 2 minus a minus c is equal to 0. This implies that minus 2 minus a minus 1, because we know what c is equal to 0. And this implies that a is equal to minus 1. And then for the length, we have minus 1 plus a plus b minus c is equal to 0. And if we solve that, we get that b is equal to 1. So now we know all the powers. Then we have pi 1 is equal to delta p times v to the minus 1, d to the 1, mu to the minus 1. Or pi 1 equals delta p times the pipe diameter over mu v. Now for the second pi group, we do the same thing. For pi 2, we have pi 2 equals the non-repeating variable raised to the first power times v to the a times d to the b times mu to the c power. Okay, and in terms of units, we have 1 is equal to length, because the units of length are length, times length over time raised to the a power, times length raised to the b, times mass over length times time raised to the c. And so again, we need all the powers to be unitless. And so this implies that 1 is equal to mass to the c times t to the minus c minus a times L to the 1 plus a plus B minus C. Okay, and as before, we need these powers to be equal to 0. So we just go through them in order like we did before. So for the mass, need powers equal 0. So for the mass, we have C is equal to 0, so that is immediate. For time, we have minus C minus A is equal to 0. Well, C is equal to 0. So this implies that A is also equal to 0. And then for the length, we have 1 plus A plus B minus C is equal to 0. Well, this is 0, and A is 0. So this implies that B is equal to minus 1. So, thus, pi 2 is equal to L, or the distance between the two pressure taps, V raised to the 0 power, D raised to the minus 1, mu raised to the 0 power, or pi 2 equals L over D. Okay. Now we know both pi groups, which is all of them in this problem. Then we have f of pi 1, pi 2 is equal to 0, or f of pi times delta p, or of delta p times d divided by mu v, and L over d equals 0. And we can rearrange this. We can yank out the pi group, which contains the quantity of interest, and set it equal to a function of all the remaining variables. In this case, that's L over D. So then doing that, we have delta P times D times mu, or divided by mu V, is equal to some function of L over D. Okay? And now for this particular problem, we can take it one step further. In most cases, you're going to have to stop here because we have no idea what this function is. You need to go to the lab to determine that function. Okay? But in this case, we know from the experiments that delta P is proportional to L. Okay? So that implies that function of L over D is some sort of linear function in terms of L. So that equals some constant K, which you need to determine, times L over D. Is basically what that implies, is that this function, which needs to be a function of L divided by D, has to be linear in terms of L. So that means in this function, it's a linear function, so it's some constant times L over D. Okay? Because from the experiments, deduce that it is some constant times L. And but our pi group says it's L over D, so we get that. So then delta P over D over mu V equals some constant times L over D, or delta P equals some constant K times mu V times L over D squared. Okay, and so this expression here, we just use nothing more than an experimental observation that the pressure drop is a linear function of the distance between the pressure taps, or the length of the tubing. And we can, and just using Buckingham pi theorem, we can deduce so much information from that. Like the smaller diameter a pipe is, the pressure drop will increase dramatically. Just like, for example, if you're trying to drink from a straw and there aren't any straws, and I'm sure you guys have done this. So you're trying to drink some soda that has ice in it, and you have a thick straw, and it's fairly easy to drink out of the straw. But if I take the same cup of soda, or pop, depending on where you are, and the only thing that is left are those tiny, thin little stirring sticks, for coffee, but those are also hollow. You know that it is very hard to drink soda from a thin little stirring stick. Trust me, as a kid, I've tried and failed. So that basically means that the pressure drop from you trying to suck up the soda or the juice or whatever it is you're drinking is much, much, much higher for this case here than it is for the nice, thick, wide straw. And so this Buckingham Pi theorem, even though it seems sort of abstract, after you do it a few times, it'll start to get straightforward. And the art of it and the challenging part of it is to determine the best set of non-repeating variables. And that will only come through experience. And so I'm going to end this lecture here.